Well, thank you, Majena, for kind introduction. Yeah, so I am from Vilnius University, and I will be presenting, as Majena said, two-dimensional sub-wavelength topological lattices for dark state ultracold atoms. So a lot of complicated words. Hopefully, I will explain. Uh, so what is context? We are usually studying ultracold physics. So in particular, ultracold atoms and optical lattices. So how cold are they? Usually a few tenths of nanokelvin. And these optical lattices, they're just made from two counter-propagating off-resonant light beams, as shown here by these black arrows. And then we get a clean, nice artificial crystal. So in theory, it is very nice. In experiment, of course, it is much more complicated, and people usually spend years working hard on it, as you can see here. So you might ask, why do people bother with this? And at least one of the reasons why is quantum simulation. So basic idea is that there are long-standing questions in fundamental physics that are difficult to study experimentally or analytically, and we have hope that we can create ultra-cold atom systems which simulate these interesting effects. And you can realize wide range of phenomena with this. So here it's like Abrikosov lattice. You can also simulate early expansion of universe. You can also realize Hubbard type models, as was said in previous talks. So here is classic paper by Markus Greiner on this Bose-Hubbard model. You can also realize longer range interacting Hubbard models, as shown here, for example, with dipolar atoms. And these lattices that I showed you, they are very nice, but they have one limitation, the so-called diffraction limit. And diffraction limit basically says that period of optical lattice has to be lambda divided by 2. It cannot be less. And why is this sad? Because if we had smaller periods, we could get faster dynamics in our lattice, and also we could get stronger interactions. But people have thought about this, and they realized that with certain atom light coupling schemes, you can achieve sub-wavelength lattices. So here you see a lambda coupling scheme. So we have a three-level system. First is coupled with excited state. Second is also coupled with excited state, as shown here with these Rabi couplings. They do not need to be resonant, so there is some detuning. And excited state has some spontaneous emission characterized by capital gamma. These lambda systems, they have zero eigenstate called dark state, shown here. And what is nice about these dark states is that they are immune to atom light coupling, and they should be pretty robust against losses. And if we are in a certain regime where these Rabi couplings are sufficiently large, then our atoms should adiabatically follow this dark state. So how do we get sub-wavelength lattice? It all depends on the change of the dark state. So as you can see in figure, upper figure on the right, in regions where the green omega 2 is largest, dark state is dominantly -2. But in this region where omega 2 becomes much less than omega 1, you have rapid change of dark state. And this rapid change of dark state leads to these sharp barriers you see here. So, okay, this is very nice. And people have made all kinds of proposals, like to make double well potentials, make random chronic penny lattices. You could go even to higher dimensions and make tunable two-dimensional lattices. And also, if you extend from lambda to tripod scheme, you could also have state-dependent lattices with sub-wavelength spacing. So this is very nice. What are we currently considering? So we are considering very particular coupling scheme with omega 1 and omega 2 as shown here. So omega 1 is a complex function, periodic, and it is shown in this B subpanel over here at the top. And it has these alternating windings. So depending on your position, it either winds counterclockwise or clockwise. And we also have omega 2, which is always real, and it is shown on the bottom here. And with this particular configuration, if you study it, you can show that you get a non-staggered artificial magnetic field, as shown here. So this artificial magnetic field has two components. It has a more homogeneous component, as shown here. And as you tune this new parameter, you get a Aharonov-Bohm peaks at specific places shown here. And as you tune this anisotropy, they become wider and wider. So this is the system we are considering. Why is it interesting? Well, let's first think, what could we get if we have nearly homogeneous magnetic field? And answer to this is, we should expect some kind of Landau physics, something akin to the quantum Hall effect. So here spectrums are shown here. And we are interested in this limit of large omega, this large Rabi coupling. So if we look here, we can see that we have approximately equidistant bands. They are, of course, not perfectly equidistant, and they have some small width. So this comes from inhomogeneities of magnetic field, but for the most part, it is similar to this Landau spectrum. And of course, as we know from integer quantum Hall effect, you can characterize these Landau bands by Chern number, and Chern number, of course, can be calculated from this Berry curvature as shown here. And if you calculate these Chern numbers, you can indeed show that Chern numbers are always equal to 1. So we should expect some edge currents in our system. So this is effect of homogeneous particle field. For these peaks that I mentioned, you have different effect. So here we see ground state density distribution in real space, and we tune this new parameter lower and lower, and what we see is phase transition. That ground state at first has vortices in the center of the system, but as we decrease this new parameter and these peaks become more and more prevalent, then we see a reorientation of this ground state. And these vortices, it is energetically favorable for them to be around these peaks and no longer at the center of the system. And this phase transition can be characterized through our system parameters, epsilon and nu. Epsilon is the scaling parameter, nu is this anisotropy parameter. As you can see in this graph, so yellow region is reorganized state, and black region is the original state, as you can see here. Okay. Yeah, so our integer quantum Hall effect, it is not sufficiently interesting, let us say. We also want to know what would happen if we add interactions into our system. And for that, there are studies shown that it is not enough for bands to have Chern number 1. If you want fractional quantum Hall physics, you also have to have an ideal Chern band. So to study this, one needs to look at the quantum geometric tensor, as shown here. And condition for ideal Chern band is that there exists a null vector for every quasi-momentum, and this null vector is constant throughout entire Brillouin zone. So we also wanted to study how ideal our system is. So for this, we took two parameters, the standard deviation of the null vector and this d parameter, which characterizes the determinant of our quantum geometric tensor. And then we, of course, plotted it. And as you can see here, we see that in certain parameter regime, both sigma and d are sufficiently close to 0. And so we can claim that we are at least very close to an ideal band, and that this quantum Hall physics should survive interactions in our system. So if you are interested for more, of course, you can come talk to me or look at our recent archive paper shown here. So conclusions are pretty simple. We can create a non-staggered magnetic field, and it can be engineered for these ultra-cold atoms from the lambda scheme that I show here. Most ideal parameters are this epsilon and nu equals to 1. Then we have most closely this Landau-like spectrum which is equidistant and has the least width. And these losses and non-adiabatic effects, they are sufficiently well controlled and they are not significant. And in experimental timescales, it should be realistic to realize this scheme. So with that, I want to, of course, thank the Vilnius Quantum Optics Group, headed by Professor Gediminas, and our foreign collaborators shown here. And I would like to thank you for your attention.
Okay, Domantas, thank you so much for this great and interesting talk. Do we have any questions from the audience? Okay, so the first one.
Thank you for the very interesting talk. I just had a quick question about when you were talking with the churn numbers. You said that in the Landau picture, exactly, you would expect some edge currents in this.
Yeah.
Have you done any simulations on that? Have you kind of like seen those at all, or have you gone explicitly searching for them, or just more that you're expecting them?
Yeah, thanks for the question. No, we did not explicitly look at this, but we are fairly guaranteed that for this homogeneous field, one should get these edge currents. But of course, it would be better to look explicitly.
And maybe another one, if I may, it's okay. When you're talking about sort of getting these like Landaus where you have these kind of homogeneous fields, is there a way to extend it to something maybe like a Harper-Hofstadter setup where you have like it's a lot more discrete, maybe like slightly deeper? So this is like nice and homogeneous. Is there any way forward to getting something more discrete, like a Harper-Hofstadter, for example?
Yeah, I did not think about this, but if one adds underlying optical lattice, in this scheme it should be reasonable to do, then yeah, I think one could also realize Harper-Hofstadter physics. But I would need to think more carefully about this. Yeah.
Thank you very much.
Usually, I mean, this dark state will give you, of course, a flat energy distribution. Usually one way to understand this is that the next band, the coupling to the next band gives you your small potentials.
Yes.
And now for your topological structure, how does the next band have to look like? Or why is it, what's there the key?
Okay, yeah, so you are right. Because of these inhomogeneities, we should have like some couplings in principle. But as far as topology is concerned, as long as these bands don't touch, then Chern number becomes invariant and it should be all good. So like for vertical cut, for example here, which corresponds to some Hamiltonian, as long as they don't touch, everything is good. For ideal Chern band, it is more restrictive. They're like, as we go from this ideal parameter regime, these metrics quickly start diverging, and yeah, then for interactions we probably lose this topology. But if we are just concerned with Chern numbers, then it should be fairly robust, if that answers your question.
Okay, any more questions? Maybe one question related to the spectra. As we see, excited state population increases in the higher energy levels as mu deviates from the unity. Why? Yes.
Yeah. So as nu deviates from unity, like our magnetic field becomes less and less homogeneous. So like one thing, you have spreading of these bands, and also we get higher and higher excited state populations. So this is also related to this inhomogeneity, but
it's an interesting result. Have you compared your results with one-dimensional sub-wavelength lattices?
Quantum what?
One-dimensional sub-wavelength lattices with dark states.
Well, in 1D it is quite different situation because there you can't have magnetic field, but yeah,
it's totally
it would
different
be
story.
Yeah, it is interesting. Yeah.
Okay. Any more questions? The last chance to ask Domantas. If no, let's applause once again for the speaker. Thank you.